So the first point we should consider there is to draw a line okay. So draw a line parallel, to the force, through the forces point of application, So that is the first step that will help us to find the lever arm. And we actually discussed last time in our meetings, we said that in a case where we have the force not being perpendicular to the displacement there, or to the distance there. Okay, so if the force is not perpendicular to the distance, we can't find our torque there. For us to get our torque, it means that the force and the distance, they have to be perpendicular to each other. That's how we defined the torque in other ways there. So now, in a case where the distance is not perpendicular to the force, then how do we find our torque there? Okay, so we came up to the idea of the lever arm. We need to find our lever arm. That is what we use as our perpendicular distance there. Okay, so now we are trying to make points simple for us, so that in a case where we forget, we can just refer to these points on how to find the lever arm there. Okay, so the first point is draw a line parallel to the force through the force's point of application. Okay, so this line here, it should be dashed. Okay, so this should be a dashed line. Okay, and this line is what we call the force's line of action. Okay, this line is called the force's line. So this, we call it the force's line of action. Force's line of action. So basically, this topic is all about the conditions or the principles are the ones which will make this topic to be very simple. Otherwise, it's very simple, provided we follow the conditions or the principles. So the second condition tells us to say that we should draw a line from the rotation axis. Draw a line from the rotation axis to the line of action. Okay, to the line of action. So we're trying to say that this line here must be perpendicular. This line must be perpendicular This line must be perpendicular to both. Okay, so move to the next screen.
Sorry, wait.
Okay, are we done with that screen?
Just a little bit, I'm coming. Let me just take a screenshot.
Okay, okay. So one was asking for the definition of the lever arm. We defined it in our last meeting, and we defined the lever arm to be the perpendicular distance from the axis, okay, to the line along which the force is acting. The perpendicular distance from the axis to the line along which the force is acting. That's what we call the lever arm there. Okay. So that is what we have. So it must be perpendicular to both the axis. It must be perpendicular to both the axis and
Sir,
yes.
sir, can you please kindly repeat what you're saying about the lever arm?
Okay, we said that the lever arm is simply the perpendicular distance from the axis to the line along which the force is acting. Okay, it is a perpendicular distance from the axis to the line along which the force is acting there. So we illustrate these points on a sketch. We'll be able to see what these points mean on a sketch. So the axis and the line of action there. So it must be perpendicular to the axis, both the axis and the line of action. So these points will mostly be applied when we start dealing with the center of mass there. The center of mass, this is where you get to see that this point of the lever arm will be mostly applicable. Okay, so the distance from the axis, distance from the axis to the line of action. Line. I'll try to use some mic here. Okay. So the distance from the axis to the line of action, to the line, or just say to the line along which the force is acting, is the lever arm. This is the lever arm. Okay, so now let us illustrate those points on a sketch. Let us illustrate those 2 points on a sketch. Let us assume we have some objects there. We have some object there, which is like that. Okay.
Sir, I'm currently drafting for the first board.
The first board?
Yes, sir.
Okay. This is the first board here. That is the first board there.
Thank you, sir.
Okay. You're welcome. So this, our axis here is at this point. This is where our axis is. Okay, so who has an idea on what other name can we call our axis there? Apart from us,
Center of rotation.
come again? Hello, repeat your answer. Okay, apart from the axis, what other name can we give this? Okay, okay. Or we could call it the pivot. Okay, we could call it the pivot. It could be called the axis or the pivot there. That is what that axis there is called. Okay, so it is very important that you know the things that you are talking about there. Because if we do not know how to define these things we are talking about, it will be very, very difficult for us to be able to solve for that thing. Okay, so how can we define a pivot? How can we define a pivot? Is there anyone who has an idea?
So just giving it a try.
Yes, go ahead.
It's a point where like the objects are balanced, they are at equilibrium.
Okay, a point where an object is balanced or at equilibrium. Okay, okay. Nice try. Nice try.
Sir,
Yes, please.
I think a pivot, okay, according to what we learned in grade 12, they said that a pivot is the area where the object is able to turn.
Okay.
That's what they said.
Okay. So the point at which an object is able to turn from there, we call it a pivot. Okay, we call it a pivot. So if we give an example of your arm there, your arm is able to turn from the elbow joint there. Okay, so you can put your pivot there. So you'll be meeting such questions also relating to the human body, where you have to apply the process or the concept of equilibrium there. Okay, so where the object is able to turn from, okay, that's where the pivot is. That's where your pivot is. Okay.
Sir,
So, yes, please. Yes. There is a question. Okay. I'm unable to get you, Cleopatra, there. Okay, so go back to our two statements that we actually came up with. So the first statement was saying we draw a line parallel to the force through the force's point of application. If we observe on our sketch here, this is the force, and the force is being applied at this point here. So this is the point of application of a force. Okay, so we draw a line that will be parallel through the force's point of application. Okay, so we'll draw a dashed line there, which will be parallel to the force through its point of application. So that is how you draw it now. That is how you draw it now. So we've drawn our line through the force's point of application. Okay, So this is what we are talking about. So this line should be dashed. This line should be dashed. And from there, you go to point number 2, which is saying you draw a line from the rotational axis. So in this case here, this is our rotational axis. This is where our rotational axis is, okay? To the line of action, okay? So you draw a line from the rotational axis to the line of action. This dotted line here is the line of action there. So if we draw a line which will be perpendicular to these axes, so this one should be a solid line. Let me just, so this one should be a solid line. Okay, so if it is able to hit that one there at that point, it will be perpendicular to that. So it will make an angle of 90 degrees. And this is what you get as your lever arm. That is what you get as your lever arm there. Okay, so from there now you can calculate your torque using the lever arm and the force now, because now the force has a perpendicular, has a displacement which is perpendicular to it. The force now has a displacement or the distance which is perpendicular to it. So from there, we are able to calculate our torque. So our torque from here will be equals to the force multiplied by the lever arm, multiplied by the lever arm. From there, we get our torque. Any question there?
So,
Yes.
so the radius, because
What? I can't hear you, Catherine. I'm unable to hear what you are saying there. I think it's the issues of network.
for torque, like there's radius in it.
Okay, now repeat your statement. Your network. I think it was cut there.
Okay. Okay, my question is on the radius. Where is the radius? Is the radius in the lever arm? Because the formula for torque includes this radius in the formula.
Exactly. So that same radius is the distance. It's the distance from the axis, from the rotational axis to the point of application of a force there. But that same force, because we actually defined our torque to be this. Okay, so this should be perpendicular to the force. These two quantities, they should be perpendicular to each other for us to get the torque. If these two are not perpendicular to each other, then they won't give us the torque. In this case, if you observe, this is our radius here, or this is our distance that we have here from the point of, from the rotational axis to where the board ends here. This is our distance there. But if we observe this distance here is not perpendicular to the force. Okay, is not perpendicular to the force. Therefore, this won't be able to give us the, it won't be able to give us the torque there. Okay, so the torque will only be calculated if the force is perpendicular to the distance or to the same radius. Okay.
Oh,
so,
okay.
All right. So we should also be able to note that we could have an angle at this point. We could have an angle at that point. So if we have an angle at that point now, it will bring us to the issue of component forces. it will bring us to the issue of component forces there. Okay, so we should be very careful on this case, whereby the force, there will be two components. You have the X component and the Y component there. So one component will be perpendicular to this distance, and the other component will not be perpendicular to this displacement there. Okay, so who has an idea on which force will be perpendicular to that displacement there? Is there anyone who has an idea on which force will be perpendicular? The force we're going to use.
Hello, how are you? Sir,
Yes. Yes.
sorry, I got logged out. I'm so sorry. I asked that question about the axis and pivot. Can you just repeat what you said from that point?
Ask your question again.
At that point, when I asked that question about the axis and the pivot, I got logged out.
Okay, about the axis and the pivot.
Yeah, can you just repeat what you said from that point to the point where you are now? I was logged out, my bundle's finished.
Okay, we only said that the axis or the pivot is simply a point from which the object is able to turn from. Okay, that's how we stated what the pivot is. At the point at which the object is able to turn from, you can call that point as your pivot there. You can call that as your pivot. So from there, we were only illustrating those points we just stated, the first and the second point on a sketch here. Okay, so the first statement is simply saying that you draw a line that should be parallel to the forces point of application, and it should be a dashed line. This is the line we drew here. And the second one is that we should draw a line that should be perpendicular to both the axis and the forces point of application. And we actually found that this is the line that we draw. We should be a solid line here. And this line is what we call a lever arm. This is what we call a lever arm there.
All right, so thank you. But what did you say about the axis? Is it the same as the pivot or it's different?
Yes, exactly. It's the same. The axis is the same as the pivot. Okay.
But I thought that the axis has to be a line.
Come again?
I thought that the axis has to be a line.
Okay, so this is the point of application, or we call this as the axis of rotation. Okay, you call this as the axis of rotation. All right. So the axis of rotation, this is what we have here. So it's the same as the pivot there. That's where our pivot is. Okay, so in this case, if we have an angle here of theta, okay, if we have an angle of theta there, you have component forces. So we have component forces. So there, the perpendicular force, the force which will be perpendicular there is the one which will cause the torque. It's the one which will cause the torque, and this will be simply F sine of theta, in that case. The F sine of theta will be our perpendicular force there, and that will be the force which will cause the torque. Okay.
Sir,
Yes.
is it that it's always F sine theta, or why is it F sine theta?
Okay. Okay, it's not always F sine theta. It could be F cos theta, okay? It could be F cos theta. So if you observe very well here, if you draw a component on this sketch, if you be able to draw a component on that sketch, you find to say that here up there like that, you have your X component force like that, up to where the axis is. Then if you move down like that, you have your Y component force. Okay, you have your Y component force there. You have your Y component force. And for you to be able to get this Y component force, you need what is known as the F sine what? The F sine theta. Okay, so the F sine theta, that is what you use for you to get your lever arm. So let me just erase this part here, so we see what we are talking about. So if you have the components of that, you have the component of this force here. You have the component X and Y component of that force. No need of using the lever arm. Okay, no need of using the lever arm. If you can find the component, there's no need of using the lever arm. You can simply go ahead and find the torque, because if you draw your X component force horizontally like that, and you draw your vertical force down like that, in this way, you find to say that this side will be found using the what? The sine. So you have F sine theta to be this side. You have F sine theta there. And you have this side here to be F cosine of theta, our X component there. So if you observe this force, which is F sine theta, it is perpendicular to the radius r, or to the distance r. Okay, it's perpendicular to this distance. So there you can just go ahead and multiply the r with the F sine theta. Then you get your torque. Okay, you get your r multiplied by the F sine theta, you get your torque. But in a case where you do not have the angle, okay, in a case where you do not have the angle, we resort to the lever arm. In a case where you do not have the angle, you resort to the lever arm. But in a case where you have the angle, it will be very easy. The only thing that you do is for you just to find your force, which will be perpendicular to this distance there. And if we observe, our Y component force is the one which is perpendicular to the r here. The X component force is parallel to this distance there. So we use this one to be perpendicular to the distance for us to find the torque. So let us take note of that. If you have the angle, it will be very easy. But if you do not have the angle, let's use the lever arm method for us to get our torque.
Sir.
Yes.
Sir, I have a question.
Go ahead.
Okay, on the same question I'd asked, I'm still not clear. Is it that she left out an error, or you said torque could be given by force and force multiplied by the lever arm? Now, is it that you left an error out there, or now this? Sir, I'm confused. This lever arm, like from the explanations I just got now, I can't say it's the radius.
Okay.
So there's no radius when the lever arm.
Okay. So the lever arm and the radius, these are two different things. Okay, so these are two different, but they are the same in terms of both are lengths, both are distances. Both are distances. So the lever arm is simply a perpendicular distance to the force. It is a perpendicular distance to the force. But the radius, it could not be perpendicular to the force, or it could be perpendicular to the force. It depends on a situation. But the lever arm is always perpendicular to the force. Okay, the lever arm is perpendicular to the force. There. This is the lever arm we're talking about. So we didn't leave out an R. Okay, we didn't leave out an R. So if this lever arm that we're talking about here, Where is that? If this lever arm that we're talking about here, this one here, if we give it an to be L, from the axis to be L there, then for us to find the torque, we'll simply say the force multiplied by the L. Okay, the force multiplied by the L will get our torque. We'll get our torque there. Because this is the distance which will be perpendicular to this force if we extend our force from the axis there, from the point of application. So we didn't leave out an arrow here. So this lever arm is not our radius in this case. In this case, it is not our radius. In some cases, it could be our radius, but in this case, it is not. Our distance simply from the axis to the force, it's this one, R here. But it is not perpendicular to the force. That is why we are unable to use it for us to get the torque.
Sir, but you said for us to get torque, the force and the